Good afternoon. My name is Ali Kujuri. I'm one of the organizers of this lecture series. I would like to welcome you all to this second lecture in the semester. And in fact, 125th lecture in this series since we started in 2006. Before I introduce our lecturer today, let me mention that at 5:30, Ms. Goodland has ordered pizza. It's going to arrive at 5:30. And then the next lecture will be on October the 5th. And the title of the talk is LiDAR Solutions Using Vernier-Tuned Distributed Bragg Reflector Lasers by Dr. Dennis Derrickson. He's the chair of electrical engineering at Cal Poly San Luis Obispo. Our guest speaker for today is Mr. Richard Halstead, and the title of his talk is The Humble Electric Motor, Enabling Science and Technology. Mr. Richard Halstead is the founder, president, and chairman of Empire Magnetics Incorporated, providing electric motors for challenging environments since 1987. He comes with many achievements, including head of wind sail vertical axis wind turbines designed by scientists and Russian State Rocket Center funded by U.S. Department of Energy, Lawrence Berkeley National Laboratory to prevent WMD scientists from working for Al-Qaeda. How about that? CTO of Power Tree Corporation, a flywheel energy storage company. CTO of Biomass to Bioenergy, director of North Bay World Trade Association, Parker Hannifin CompuMotor Division, Western Regional Sales Manager, Linear Motor Product Manager, Manager of a Special Projects Department, and so on. So it's my pleasure to have him here, and he's now he has the floor now. Okay.
Thank you. Before I start, a couple of very simple things. Would you raise your hand if you are an engineering student? Okay, now I know. How many of you are electrical? Any mechanical? Okay. Next, I wear hearing aids, so if you ask a question, speak up. Other than that, we're ready to go. Somebody's been pushing buttons. Okay. My company makes special electric motors. We don't do the standard ones. We sell through an international distribution network. Almost all of our distributors have supplies from large companies like Emerson, Cole Morgan, Parker Hannifin, Baldor, you name it. So if a customer needs a standard motor, it ain't us. Typical little motor goes for 150 bucks, 250 bucks. Our lowest cost motor goes for 1,500. The most expensive motor we've ever sold, actually a motor assembly, $182,000. A lot of engineering in that one. Okay. This is just to give you a flavor of what we've got here. Space rated, abrasive materials, more abrasive materials, cold temperatures, hot temperatures, cryogenics, washdown applications. Some of the people behind all this, that's me first. Dr. McClellan used to be the president of Parker Hannifin CompuMotor Division. He's still on our board of directors. We spun off from CompuMotor in 1987. It was a very friendly relationship. Dr. McClellan went on to be a buyer of companies for Parker Hannifin. So I have some access to people who know a little bit about business. Dean Weinberg is a technical project manager at Jet Propulsion Labs. So we have access into the NASA network when we need it. Mr. Viali was our first investor and is also a superior type salesperson. If you're looking for the website, there it is. It's also on these little brochures that I've passed around. You may ask, what does Special Motors have to do with this kind of stuff? I will tell you about the linkage later, but the reason I put this slide here now, if you notice on the bottom of each slide, it says Lawrence Berkeley National Labs and the Makiev Rocket Center. This photograph right here is taken at the State Rocket Center in Mias, Russia, where we were building this vertical axis windmill. This is also another vertical axis windmill. This gets us into the biomass thing. I will expand on that later. But that's why I have this notation on the slides. And to be honest, I was too lazy to change it. Automation and motion control. By the way, I was asked to explain what the job opportunities were in this marketplace. This is one of the fastest growing industries in the world. We're talking robotics. We're talking all kinds of miniaturization, automation, you name it. A distinction. We do motion control. You will find a whole nother area called power transmission. Power transmission is about pumps and fans and chains and sprockets and belt drives and things like that. We don't use that much. We're into, can I position to a micron? You know, can I move a robot arm? Can I point an antenna on a satellite? Whatever. Much more precision type motion control. Some of the jobs, not all of them. Applications engineers. Every distributor needs at least 2 or 3 applications engineers. I have, I don't know, 1,500 different sales offices around the country, distributors. They're all looking for applications engineers. In fact, I belong to the Association of High-Tech Distributors. I'm going there next week. And one of the topics is, where do we find qualified people? Now, the part you're not going to like, 70% of the US economy is selling something to somebody else. This whole business is selling. They may call you an applications engineer, but you're going to have a sales hat. You can be a sales engineer, you can be a project manager, but somehow you're going to interact with the customer and you're going to have a role in selling something. There are very few positions back at the factory where you design things, make things, and nobody sees you. Most of those factories are offshore. In addition to all of the technical positions, you got all of the normal back office things. Accounting, bookkeeping, invoicing, you know, HR, keeping up with the insurance payments, and don't forget all the governmental forms. They never stop. As I said, we have a national and international distribution network. If you go to our website and you click on Contact Us, up pops a map. You can click on any country or any state, and under that country or state, you'll get a list of our distributors in that area. I'm not claiming we have the world covered. I certainly don't have anybody in Pakistan or North Korea or Iran, you know. In fact, probably would get in trouble if I was trying to ship some of my stuff there. Over the years, we have had a number of interns. And by the way, yes, I do have a couple of intern positions open. This is what has happened to these people as their careers have progressed. Walter wound up working at Lawrence Livermore National Labs. He is designing equipment for the National Ignition Facility. Mark went to work originally for the GE Nuclear Division in San Jose, wound up being a plant operator in Japan, and now is working for Arriva. Andre went to work for Daimler Chrysler and wound up in supply chain management. Sierra originally went to work for Hewlett Packard, moved to Lockheed Martin, was at the Santa Maria facility at Vandenberg, transferred to Cape Canaveral, was doing facilities support for the shuttle launches. She could go as close to the shuttle as it was possible unless you were an astronaut. Later moved up and she was running the flight simulator department for the F-35 down in Fort Worth. Mark Miliano is at China Lake. He's working for the US Navy doing product development. He calls me once in a while for motor assistance. Alex went on and got his master's in business, and he is now a partner in a venture capital firm out of London. Ava was a student who came originally from Slovakia, I should say Czechoslovakia. While she was here at Sonoma State, the country split into Czech and Slovakia, so she had a problem. She couldn't leave the USA because there was no visa project for Slovakia. As a result of that, she became quite an expert in all the international visa stuff. And so she was processing all the international students coming into Sonoma State. She later went on, got her master's degree, and now she's doing the same kind of job for the London University in London. Jörg is working for one of the largest banks in Europe. He does technology assessment on major projects when they're considering them for loans. A few little things that you might recognize. Some of you may know of Flex Technology. They are right up here in Santa Rosa. They make the color-changing ink. They were originally Flex, then they got bought by JDS Uniphase, and now they are Viave. The color-changing ink machines are based on our motors. Without it, they wouldn't be able to make their product. If you've heard of the binocular telescope being built at the University of Arizona, a whole bunch of our vacuum-rated motors all through that thing. You may remember that the space shuttle blew up on launch. The reason was that the O-rings on the space shuttle became too hard and were not sealing. So shortly after that, I got a call from Martin Thiokol and said, we need to be able to test the O-rings on the space shuttle while it's sitting on the launch pad. So we designed up something called the penetrometer. It had to be able to measure the durometer of the O-ring. It had to be safe, it couldn't blow up, a whole bunch of requirements, but we did it. Another one, let's see, this guy here. The nuclear fuel processing for the US Navy submarines. Remember this $182,000 motor I was talking about? Well, once you put the motor into that facility, it never comes out. It's contaminated with some really nasty stuff. So they had to test it. It took 4 years to qualify that thing. Now, this was a neat little one. During World War II, the US Army built a large number of chemical weapons. They're outlawed now, but they had these things in a stockpile in the arsenal there in Salt Lake City. And I mean in the city. One half of the thing had solid rocket fuel, and the other half had the chemical agent, and they were housed in an aluminum structure. Well, the chemical agent would eat through the aluminum, and when it did, it would attack the solid rocket fuel. This thing would ignite, and suddenly we have this thing bouncing around inside a bunker with thousands of other ones just like it, spraying chemical, nasty, really nasty chemical stuff. So the Army said, okay, our solution is we're going to load all this stuff onto trains, we're going to ship it to the Port of Oakland, we're going to send it up to the Johnson Atoll, and we're going to burn it. And one of the senators for California said, now let me get this straight. You're going to take these unstable poison rockets, you're going to ship them through my state to a major city in California, and if they happen to go off, you're going to kill a few million people? No, you're not. So we got a call from Stone and Webster, an engineering firm back east. We need to do this. So we had to make motors that would work in this absolutely amazing chemical goo. It would eat almost everything. And what they did is they made a tank in a trailer, drove this thing to the place, and then they would start loading these munitions in there and cutting them open, and our motors were running the robot arms and so forth to get rid of this stuff. NASA launches weather balloons from the South Pole. We have motors that are on those weather balloons. In addition to that, we have a number of motors actually installed down there at the weather station. One of the guys who used to work in my company worked with the group out of University of Wisconsin that maintains all this, and he literally went down there, and this was back before internet and so forth, so I had an ISDN line. I was the communication channel while he was down at the South Pole between him and his wife. In the International Space Station, in the human habitation areas, there are lab modules where they have all these tests going on, and there are fluid flow control valves. Every one of those lab modules has one of our little motor gearbox assemblies for the fluid control valve. The calibration system for the long-wave X-ray telescope, Chandra, uses one of our motors to move the calibration source across the face of the scintillators. We have built hydrofoil flap controls. We're talking huge ship flying over the water 40 miles an hour, amazing amounts of torque. This one's kind of cute. Do you think there might be any safety issues, spray painting, hand grenades? Woods hole, 2,000 meter deep in the ocean, got that going. The downhole well units, I'll get into that some more. This one, we got a call, this was 20 years ago. Can you make a motor 230 degrees centigrade, massive doses of radiation, and oh, by the way, it's under liquid sodium? We said, well, we can do the first two, but not the last one. And they said, okay, we'll build an enclosure around it. So we did. We built a motor assembly that handled all of that and wound up in the heart of the fast breeder reactor in Tokai Works, Japan. This slide, a marketing problem. How do you take a picture of a vacuum? Think about it. How do I advertise my vacuum-rated motors? And, you know, we got artistic. This is some piece of equipment from a vacuum chamber. And, of course, you know, you get the space image there. We've done all kinds of satellite programs. In fact, one of the big markets opening up right now is microsatellites. As a result of SpaceX, The world has decided that the way to handle communications and all kinds of other things, instead of putting up one big expensive satellite, let's put up a couple of hundred little ones. If you lose 2 or 3, well, you're still in operation, you know? By the way, because there's quantity, let's make them cheap. So there's a lot of pressure to bring the price down. You know, we're no longer doing multi-million-dollar projects for NASA. You know, we're doing $1,000 motors and stuff like that. We have done ground support and testing. Hughes Aircraft was building a military satellite, which I didn't see. We had to rotate and tumble that satellite continuously for 70 days in a vacuum. In order to keep the motor from overheating, we devised a mechanism to take the vapor from liquid nitrogen and pump it through the motor and control the temperature by how much flow we did. So we managed that. We have several motors on the space station. When the shuttle used to come up to the space station, they had a docking ring. Originally, the docking ring didn't move. Later, they made the docking ring move about 4 to 6 inches, and then there were these clamps that locked the shuttle in place. My motors, my clamps. We will get into beamlines, observatories. Most of the observatories in the country now have a vacuum at that last couple of meters. So the air in the area where you're working doesn't distort the images. So we get a lot of business out of observatories. U.S. Naval Observatory, we've got motors on the Subaru telescope, Mount Keck, Lowell, I can't even remember them all. Lots of semiconductor manufacturing. The cleanest clean room is a vacuum. There's no air to make the particles float around and get things dirty. We also get into vacuum casting. Imagine a 30,000-pound rail car full of hot metal rolling into a place so they can pour it into molds in a vacuum so there's no air bubbles. We're doing that too. The International Space Station, on the external part of the space station, there's a device called CATS. It was installed about 1.5 years ago. The Wake Shield lab module was launched and recovered 3 times. We had momentum controls on that. I told you about Chandra already. BSAT-2, that one was interesting. Our assembly had to operate during launch. And it was a real challenge because it had to be a certain size and a certain weight and all kinds of things. We get a fair amount of business out of NASA Goddard, the Marshall Space Flight Center, the vacuum qualification system down at the Marshall Space Flight Center has our motors in it where they're testing to qualify other pieces of equipment in the vacuum. JPL recently purchased a motor from us for the gas sampler that they intend to send to Titan, the moon. This is a lovely little picture. That is a jet engine under test aboard the aircraft carrier Kitty Hawk. Our motors are controlling the fuel valves. There's a whole system there called SETI. I forget. We've shipped, I don't know, 90 or 100 of these things, something like that. This is about the O-rings on the space shuttle, and this is just a pretty picture. Getting down to earth, waterproof motors, weatherproof motors, get into pipeline controls, fish hatcheries, food processing. There's a place over in Modesto that makes hot dogs on a stick. Imagine, you got to swing the hot dog into place, you got to take the stick, and you got to poke it in there. How many can you do per hour? A whole lot of them. Drug manufacturing, they have to wash down every 4 hours and sanitize and so forth. If you've ever seen the water show at Cirque du Soleil, this piano moves. That motor moves that piano.
How big is that motor, by the way?
That's about 10 inches in diameter and maybe a foot and a half long. A little story on this: when they first got it, they got everything all together and they called us up and they said, "It doesn't move." What? Turned out that they had the thing sitting on a carpet, and the wheels had indented the carpet, so it was sitting down in a little bit of a ditch, and they couldn't get it going. They had to get rid of the carpet. Navy submarines, the naval labs. There's one in Maryland. There's another one in Indianapolis. We do various research, ROVs. Oil wells. This one's interesting. Let's go down 15,000 feet. It's only 150 degrees centigrade. The cable, round trip, 30,000 feet. You can only have a 14 gauge wire because if it gets any bigger than that, we can't spool it up and down the well. Your unit can't be more than 1.3 inches in diameter. Can you give me 200 inch-pounds of torque? Oh, by the way, we're going to set off explosives in the well. I'm serious. When they drill wells today, they make a concrete casing as they're drilling down. After they get done drilling to a point where they want, they pull everything out and they send sensors down and they determine where the oil or gas is at. They then put down in the well the equivalent of a claymore mine. It's basically explosive with ball bearings. And they locate where they want it and they set it off. Bang, you know. We get these back every so often with all the teeth gone out of the gearboxes. This is another one. The Swedish Navy decided that they wanted to go searching, at least we were told, for mines. And the idea was that they had an umbilical cable 800 meters long on a destroyer, and they had this little mini submarine that swims around and looks for the mines so the destroyer doesn't hit the mine. Okay, but then they wanted it to be able to point to 1,000th of a degree. And I'm going, wait a minute, this thing's out in the ocean, floating around in the water, moving like that, and you want to point 1,000th degree. Are you crazy? No, we'll pay for it. Okay, you got it. That one is the drill motors that go on the submarines. They use them for basically doing mechanical operations on the submarine. This is the one that goes into that god-awful mess I was talking about. It's actually a servo motor, a resolver, a giant gearbox, all special materials, radiation hardened, chemically resistant, so forth. This is just to give you an idea of what goes on inside one of these little guys. Yeah, there's no complexity to it. The U.S. Naval Labs, this unit goes into their test tanks. They're in Maryland, 5,000 PSI pressure. This thing has actually come back to us for a rebuild after being in operation for 15 years. They're very happy with us. Woods Hole, I identified that one. Scripps has got them. The Undersea Warfare Center, China Lake, all of these guys have waterproof stuff. The vacuum casting thing I was talking about, there's the gearbox that went on the rail car. This one goes into a beamline, and I'll get to that in a minute. The drill motors we've already talked about. Radiation hardened motors. You go, well, the nuclear industry is pretty much shut down. Why would you want radiation hardened motors? You remember a little place called 3 Mile Island? How do you clean up that mess? radiation hardened motors. Oh, can you make them waterproof while you're at it? Yeah, we did that too. Fukushima, Westinghouse came and said, can we have some waterproof radiation hardened motors real quick? But more importantly, Beamlines. Now, most of you are going to go, what the heck's a beamline? This is the beamline at Stanford Linear Accelerator. You see this long tube here? That's a vacuum, and they're accelerating particles down that tube. Now, there are facilities like this around the world. Some do neutrons, some do protons, some do X-rays. They all produce radiation. If you look carefully, you'll see motors here, motors there, motors over here. There's motors all over this place because they have to precisely position things. They have to be subjected to the radiation because they're close to the beam line. And some of them are actually inside where they want them both vacuum and radiation. That's a tough one. Now, going back. Some of the beam lines that we have worked on, the National Ignition Facility at Lawrence Labs, the Advanced Light Source at Berkeley Labs, the Stanford Linear Accelerator, ANSTO is the Australian group, OPG, I gotta remember what that acronym stands for, it's one of the labs. The guys in Australia have been using our motors very extensively, and they, like this one is a brake and a motor and a gearbox. These are special little resolver assemblies. They wanted these crazy connectors on them. We said, but the connector's bigger than the resolver. They said, it's okay, you know. This is just a table of all of the different things that went into the one facility there in Australia. You get a tally of how many and what they were. Some of the people who are looking for this combination of radiation and waterproof, GE San Jose, we're doing reactor inspections. You go, now what's that all about? Well, it turns out that almost all of the reactors are built with a double wall arrangement. And there's a space about that big between the two walls. They figured out if they can put ultrasound equipment down in that little space, they can look for cracks and crevices and all that sort of thing, and they could recertify the containment vessel. If they can recertify the containment vessel, they don't have to spend $400 million tearing down the reactor, and they get to make a few $100 million more of selling electricity for a few more years. So when we told them, yeah, we can make this motor, but it's going to be really expensive, they said, we don't care. Just make it. And there they are, right there. Ontario Power Generation out in Canada uses our motors, Texas Utilities. By the way, Westinghouse, you probably have all heard that name. Did you know that the Westinghouse nuclear division was sold to Toshiba? And Toshiba went bankrupt just a few months ago. The whole Westinghouse nuclear thing dismantled. It's not there anymore. I'm now getting calls from Argentina. We've got one of these old reactors and we need blah, blah, blah. Can you give us anything? So it's interesting. Temperature extremes, generally speaking, our motors on the high end, we're using a Class H insulation. That means that the insulation begins to soften at 180 degrees centigrade. The motor itself typically has about a 50 degree C rise from the current flowing through the windings. So it means an ambient temperature of about 130 degrees before things start to go bad. As I said, we did make a special motor for the fast breeder reactor. Back when we did it, it was like 50 grand. I'm sure today it would be 250 to try and duplicate it if we could. Some of the vendors that we used are gone. On the low end, we have done motors that run at 4 Kelvin. That's 4 degrees above absolute zero. You don't want to stick your finger in there. This little guy here, they wanted to rotate a satellite. They wanted to be able to point it with extreme positional accuracy, all while it's in a test chamber, vacuum, and super cold. So what we came up with is this thing's here on a hinge. That's a magnetic coupler, and there's a magnetic wheel here. So when they came together, you had a hard surface, steel to steel, no slip, because the force to turn this thing is next to nothing. So we were able to give them the positional resolution and accuracy they wanted, all while it's super cold. Now, by the way, this picture right here, nobody does that. This is strictly for a magazine. You don't put your really expensive equipment in an area where it's going to get loaded up with ice. By the way, carbon dioxide freezes too. For Sandia National Labs, this one only went to 24 Kelvin. Subaru telescope. This, I got a call from the University of Hawaii. Dr. Brown said, can I get one of your cryogenic motors? I said, sure. He said, can I get it quick? I said, no. And I started to tell him, about all the advantages of our motor. And he says, I know, because right across the hall from me is the Subaru, and they put your motors in there, and it's working, and the one I got, not working. So I know that we're having good luck with Subaru indirectly. Dust proof, we get into all kinds of interesting things, sawdust, paper dust. Then you get into things like flour mills. Did you know that flour is an explosive? Oops, wrong button. Abrasive resistance. One of the early customers for our products was a place called Atrax. And what Atrax did was make these carbide burrs, these little tools that you buy that have the spiral cut burrs. They're made out of silicon carbide. Well, they were using our motors to make those burrs with. Another company, Corning Glass, they started out to make something, it was called fiber optic. Nobody knew what it was at the time. They started having all kinds of motor failures and found out when they were making this fiber optic, there's little bits of glass floating all around the place and getting into the bearings and tearing things up. And we thought, wow, our motors are failing after a month or so. Something's wrong, And we went over there and talked to them, and they said, we're delighted. The other motors were only lasting 3 hours. So we eventually got it fixed, and motors last a whole lot longer now. Explosion. In North America, there are 2 versions of explosion proof. One is what is well advertised, known as explosion proof. It comes with a certification from UL Labs. The origin of explosion-proof motor is World War II brushed DC motors pumping gasoline into the fighter planes. They needed some way to keep the thing from blowing up. A brushed DC motor has arcing and sparking as the thing goes around. So the technique they came up with is we make this big, heavy cast iron housing. It's got a whole bunch of labyrinth ports in it. And we know the volume, we know what the material is that's going to blow up. So we made it strong enough it'll withstand the expected explosion, and the mass is enough to cool the gas so that the explosion doesn't propagate outside of the vessel. Explosion proof. Not exactly what most people think of when they don't want something to explode. Now, to get this UL certification, I call UL and I say, I'd like to get my thing certified. And they say, okay, send me a check for $30,000. It'll take about a year and a half. If you've done everything right, we'll issue a certificate so you can go negotiate with the insurance company as to what your insurance rates are so you can sell explosion-proof motors. The alternatives. National Electric Code, Section 70, subsection NFPA 496. If you take a device and you pressurize it with a known safe gas, you can operate it in an explosive area. This one has a much older history. You go back to the coal mines. The early coal mines had problems with things blowing up. So they learned that if they took something, put it in a vessel, and pumped clean, dry air into it, it wouldn't blow up. That worked its way through the guilds and then the trades and eventually wound up under the control of the local fire marshals. The National Fire Protection Association is an association of fire marshals. They get a whopping $25 for their pamphlet, NFPA 496. And the fire marshal in the local area where you're at that inspects your equipment gets a fee for the inspection. That's it. The catch-22 on this is it has to be installed and certified locally. There's no way I can issue a piece of paper in California that says if you install this in Chicago, it's just fine. No. You install it and get the fire marshal in Chicago to inspect it. We're talking about spray painting hand grenades. There it is. Another one. I got a call from Morton Tackle, and the guy says, can you arrange a motor that does this? And he said, we used to have this, and now it does that. And what are we talking about? And he says, well, we take and we pour liquid rocket propellant into these molds, and then after it solidifies, we have to push it out. We call it a core popper. Now, when we push it out, if we push too fast, the friction will ignite it. If we push too slow, it sticks and it fractures, and then we got to redo it all. There's a large hole in the ground where our core popper used to be. They were using hydraulic systems first, and they kind of lost control. You know? They came back and said, you know, electrics are much better. We get into some custom designs. This one was for NASA. What they wanted was 2 motors on the same center line, counter-rotating, where they could put optics, and they were going to run a laser beam through it and make a scanner. The plan was to map a planet, territorial mapping of a planet, you know, looking at the geometry of the surface. This is a medical system. They were using it for brain surgery. And they had to sterilize it, and the doctor had to plug it in and all that. The standard method of getting linear motion is to take a rotary motor, hook it to a lead screw and a nut, and turn it so that it gives you linear motion, or linear translation. The advantage of this is you get a lot of force. You get the mechanical advantage of the screw. The disadvantage is it's slow. This thing is called a linear motor. The advantage of it is it's very fast. These things, when they're moving, are just a blur. You can't see them. But they don't have a whole lot of force. Dr. Stodnick, please.
That's kind of like a railgun, right?
A railgun works on the same principle,
Yeah.
yes. Okay. Dr. Stodnick has designed a way to get twice as much force in the same physical package as what's on the market today. He's trying to build a factory to make this happen. Long story short, he started out trying to do this back in 2008 when the stock market tanked and everybody was running for cover. He wound up going to the Russian government, convinced them that they needed to invest in their machine tool industry because they hadn't done so since 10 years before the Soviet Union collapsed, so they're like 50 years behind everybody else in the world. It is now an official program by the Russian government. The Minister of Industry and Trade is personally tracking it. Sistema is a London-listed stock exchange company. They're doing the equity part of it. The Russian Soviet bank, or sovereign bank, is going to take care of the capital equipment. Has anybody heard the word sanctions? Might be a problem. Okay, motors from scratch. How many of you have any clue how a motor works? Anybody? Okay, got two, all right. The basics of a motor are very simple. Put in electricity, take out mechanical power, and heat. The limit of how much you can put through that device is how much heat you can get out of it. This is some computer modeling. This particular one is about the magnetics. You can see this is Tesla's here. This is an axial gap motor design. Here's another axial gap motor. And you go, okay, what is he talking about? Most of the motors that you're familiar with are what we know as radial gap motors. You have a cylinder within a cylinder. This is the outer lamination. The windings would go in here, and then you would have a rotor inside of that. That's a typical radial gap motor. And you're looking at this and going, why is it all these little pieces? Well, there's something called eddy currents. When you run a magnet past a piece of metal, you get eddy currents circulating. If you don't make all these laminations, you get a lot more heat and a whole lot less efficiency. Now, an axial gap motor works in this arrangement, where you have the magnets facing each other and the windings are in between. So you can see the air gap is in an axial plane as opposed to the rotary. Here we have lamination. It's basically a strap. You just wind it into a coil. And this is a laser cut piece here. One of the problems in the existing marketplace is the laminations get punched out of sheets of metal. The bigger the motor, the bigger the sheet of the metal. The cost of the material is going up as the square of the radius. The punching dies go up as the square of the radius. So bigger motors cost a whole lot more. And when they get really big, they cost a whole lot more. Yes, we can use laser cutting to avoid the punching dies if you're only making a few units, but it's not very efficient. There is a problem also with the bearings. Let me go to that. If you're looking at large diameter bearings, I'm talking anything over 3 feet in diameter, they get crazy expensive because this piece of steel here has to be precision ground after it's been cast and machined and all of that. There's another problem. These little balls that are in here, depending on the diameter and the ratio of the diameter of the little balls, that ball is turning a whole lot faster than the big ring. Well, eventually you hit the point where the ball either comes flying apart or it starts to skid. It's no longer rolling. So a typical big bearing like this, top speed's about 400 RPM, something like that, maybe even 200. Another little clue, the life decreases the square of the speed and the cube of the load on the bearing. Okay, you may wonder, how did all of this special motor stuff get involved with windmills? You need an alternator on windmill, right? An alternator is nothing but a motor run backwards. If I put the mechanical energy in, I get the electrical energy out. Still got the heat problem. This is the magnets on this hub here, and that's the winding. This particular unit is a vertical axis windmill. The general concept was mine. This whole team here is at the State Rocket Center. The guy in the middle is Dr. Del Baca from Lawrence Berkeley Labs. I wasn't there on that particular day. This whole thing is a 3 kilowatt unit at 25 mile an hour wind speed. Now, you may ask why. You see this? That is the very first submarine launched ICBM that the Soviet Union ever built. After they launched it, they recovered it and they made it a monument here at the Mias facility. This is some of the toys the boys were playing with. During this period, Al-Qaeda was running around with suitcases full of money, and Russian scientists were selling their shoes in order to have something to eat. Some of us decided this was not a good situation, and so I wound up being in charge of this program. I had 110 PhDs at the Russian Rocket Center designing those windmills. And that's me standing right there. These other gentlemen right here, I can name all of them except that guy. He's the man who took care of all my security needs. As far as I know, Dr. McClellan and myself are 2 of 4 Americans that were ever at this place. It is now closed again. You can't go in. One of the things they have here is a water tunnel. It has both a horizontal and a vertical section. And it's about 2 meters across here. When they want to pump water, they call the dam and say, start letting water down, because it takes 2 megawatts to run the pump. This is stress analysis of this blade that was being tested. We did initial tests on stainless steel versions in the water tunnel. Okay, I'm told that we're getting down on time. There is another type of motor known as a synchronous reluctance motor. It doesn't have the permanent magnets, it's all iron and copper. And the reason it's important is because NASA used this type of technology to come up with what is known as a bearingless motor. There is literally no mechanical bearing. It turns out that if you take a normal motor, when you energize it, it acts like a solenoid. And so you've got an attractive force this way. I mean, you try to pull it out and it doesn't want to come. All we had to do was figure out how to keep it centered. And NASA did that. Ralph Jansen came up with the patents on it. And they decided they were using it for flywheel energy storage. And this is the prototype for the bearingless marine. We also got into biomass. You go, what does biomass have to do with motion? Well, it turns out if you want to take biomass and turn it into methane, you would like the little microbes to be able to get at the mass. If you can grind the mass, chop the mass, make it really small particles, the process is faster. This stuff here is hydrilla. It's an invasive aquatic species. It's clogging the waterways of the American South. Florida spends like $400 million a year cutting the stuff, trying to keep it so the boats can get through. This is a plan for a zero-emission power plant. I won't get into all that right now. My last thing is success. You can have vision, you can have skill, you can plan, you can organize, you can staff, you can work hard. But if you're not in the right place at the right time, it doesn't happen. And I can tell you from experience that when Russia invaded the country of Georgia and our windmill project went down the drain, I didn't have anything to do with that. All right, questions? Anybody?
You make a lot of these motors yourself, or all of them, right? You must have quite a machine facility.
Actually, we do it all
Or you
by
send it
supply
out.
chain. We do the engineering, material specification, final assembly and test.
Okay.
The actual manufacturing is all done by larger motor companies,
Okay.
and we buy parts from them.
Okay. The other question I have is, a long time ago, I worked on a rad hard project in electronics. But what do you do to make a motor radiation resistant?
Materials.
But this is all in the material.
Particularly materials. An example, don't use Teflon.
Yeah.
Teflon in a gamma radiation releases a cloud of toxic gas, and it's gone almost instantly. You go to something like Kapton or polyimide, and now you can get 10 to the 9th rads before it's gone.
Okay.
Nobody else?
Yeah.
Are you guys involved mechanical engineers in your process of designing the motors?
Absolutely. Mechanical engineering is about 80% of what we do. Almost always the initial selection of the motor is done by the mechanical engineer who says, can you make it fit here? And we get into the specs of how much torque, how much speed, what accuracy, and all of that. The electrics generally are later in the process. You know, can we program it? Can we get the resolution we want? Do you have non-volatile memory? Is it absolute or is it relative? You know, things like that. Next.
Where are you guys based out of?
Right here in Owner Park.
Yeah, well,
We're on Commerce Boulevard. The address is on these little brochures. If you didn't get one, let me know. Yes?
Why is the vacuum environment such a challenge?
Have you ever seen one of these experiments in high school where they take a beaker of water, they put it under a bell jar, and they pull a vacuum and you watch the water boil until it freezes? Never saw that.
Afraid not, but I understand.
Okay, well, other materials outgas as well. It depends on what material you have used as to what the outgassing rate is. Now, you know, a piece of steel doesn't outgas very much. On the other hand, some of the adhesives that you might commonly use, like a Loctite or something, goes away very quickly. Okay?
So you have to deal with that byproduct.
We have to choose all of the materials for the environment, and we also have to be able to verify that we use those materials and that somehow we can convince our customer that, yeah, we use the right stuff. NASA, for example, issues a document called 022A 1124, which is a list of all of the materials they've ever tested for space and so forth. And if you can show that in their chart you have chosen a material that they say is okay, then you're good. Another issue you get into on satellites, for example, is lubrication and mission life. If you have vacuum grease and you have a mission life of a couple of years, you're probably good. If you have a mission life of 15 years and you're headed out for one of the outer planets, not going to make it. You got to go to a dry film loop. Anybody else? Yes?
Yeah, what kind of environments do you have set up at your facilities and run your parts for testing?
Actually, very little. Most of the testing is done by our customers. It's a business decision on their part. They don't want to pay for me to do the testing so that I can sell the product to somebody else. They want to do the testing at their facility so they can sell their equipment or their system and not have the competition.
And then,
Yeah, go ahead.
oh, are most of your final products sold to the same people? Like you pretty much custom design a product for certain companies, or?
Obviously, we do get some repeat business. For example, the Australians, Dr. Frank Darman heads up that project, and he not only does the Beamlines for Australia, but he's deeply involved in the European Beamlines, and he is recommending our products for some of those other facilities. The vast majority of our customers, however, are one-off. They got a contract, you know, it's done. We'll call you if we need you again next time. Back there?
Can you talk about the internship opportunities for students? Can you talk a little bit about the internship opportunities for students?
Okay, interns. We have a couple of different possibilities. Right now, we are in the throes of transferring our computer integrated manufacturing software from one system to another. That requires that we take all of the engineering data and put it into the new system, restructure it, clean it up, and so forth. So there's a case where somebody with some technical background and willingness to work on a computer would have something to do, and when you get all done, you're going to have a pretty good idea how we make our products. Also, we're looking at some engineering type talent, probably mechanical, because most of the stuff that we do requires CAD work. Enough?
Okay, it's now 5:34. No, in fact, 30. Yeah. Okay. I'm sorry that I need to leave, but if you'd like to ask more questions, please do so. I would like to thank Mr. Halstead for his very interesting talk.